And this is a very popular one. Lucretius lived in the 1st century BC and actually has a few chapters that describe things such as what seems to be Brownian motion. We don't know quite exactly what he meant, but he was looking at motes of dust inside sunbeams. So this constant state of motion is something that we are generally thinking about when we use physical physics or liquid crystals or polymers in some kind of solution. So I'll just read, because it's quite small. Thou turn thy mind the more unto these bodies which here are witnessed tumbling in the light. So he's describing something he's seeing in a sunbeam. Namely, because such tumblings are a sign that motions also of the primal stuff, secret and viewless, lurk behind. For thou wilt mark here many a speck, impelled by viewless blows to change its little course, and beaten backwards to return again, hither and thither in all directions around. Now that's a description of Brownian motion as we understand it, okay? Encoded in rather beautiful language, and something we base a lot of the ideas of what is happening in the systems that we're describing in this part. We've seen some introductions to polymer chains, the mathematics and the physics of some polymer chains. So here's a very large polymer chain. It used to be a polyelectrolyte, now it's just a polymer chain. And these things can take on a lot of configurations. And speaking about their configurational freedom, we related that to the entropy, and via the expression for the free energy could deduce relationships between the extension and the force applied between the ends of the chain. Also got a probability of how likely it is to extend a certain chain consisting of a certain number of segments to a specific length. So we all have this idea that if we're taking a look at a very small polymer chain, that you can pull on it and it pulls back. And in the ideal case, it looks like a spring. Okay, this is the entropic argument. Of course, it's completely right. Where do you think does the force come from? Can you imagine another way? So we've got this entropic argument. As somebody said yesterday, it's quite an abstract quantity. It's causing the force between the two ends of the polymer chain. I'm holding this polymer chain, and you imagine that it is a lot smaller than this. So we've spoken about the entropic origin of the force. What does that mean? What's happening so that I'm experiencing force? So that if I were doing some of the clever experiments, we'll probably hear about that this thing was to pull my hands together if it's a polymer chain. Any ideas, any suggestions? Well, you should say entropy, okay. What's another perspective here?
The environment.
Yes, the environment. These things are swimming around in a fluid. So these are tennis balls, represent particles that are constantly being hit by the surrounding fluid. You can imagine that I'm holding this. Each one of you were to grab hold of one of these tennis balls and jerk them to and fro. My hands would immediately approach each other because I'd be experiencing a force due to the constraint of the connectivity of the chain. So a very simple illustration, of perhaps too simple-minded. You have a Brownian particle hitting some kind of object. It bends, contracts because of some geometrical constraints. And then, of course, you can think about filaments of different levels of bendability or flexibility, as were described in another lecture. Okay. So we've got these basic ideas, and the important concept is that these filaments have some intrinsic elastic properties and that they certainly exert forces. Okay, so what I want to talk about is the idea of creating a network out of filaments. Mark explained very beautifully and showed us the example of rubber elasticity with latex from the rubber tree and how Goodyear managed to cross-link that and so on. So I want today to discuss a little bit more in depth some of the questions we need to ask in order to start doing calculations and in order to understand what is going on in these systems. There are many different types of networks you can imagine. There are the ones that Mark illustrated where you have very flexible polymers connected by a few cross-links. You can think of something consisting of filaments built together, so of units building filaments, branches occurring, and then some kind of tree-like network emerging from that as more branches form. This, for example, might happen in certain instances within cells where you have certain types of filaments that can cause branches, so typically at a specific angle, and you can get this kind of tree-like network out of rather stiff filaments. You can imagine that perhaps a tree network, if I were to squeeze it, has a certain amount of elasticity, but that might be quite different to the elasticity if I have very flexible polymers that are in this kind of fisherman's net configuration. Okay. So the idea is to bring some focus to these questions rather than to answer all of them. Okay. I'm going to leave that for a while and do a little bit of stuff on the board. So let's start thinking about the simplest possible networks that we can form. We said that our basic element, the flexible polymer chain or any other version of the polymer chain, might, in some or other approximation, just stretch it a little bit, look very much like a normal spring. So you would have a normal force law of a spring with zero extension under zero force, and some spring constant K playing the role of the force in this element. And then we can play high school games and figure out what happens if I take one of these springs and I couple it to another spring that is identical. So both springs have the same spring constant. What is the effective spring constant of the combined two springs? Remember that one? High school, first year, somewhere around there. Does it have the same spring constant? Does this spring become harder or does it become softer? So we don't need clickers. Who says harder? Okay, so everybody says softer. Good. What happens if I missed that? Oh, you don't know. What happens if I rearrange these springs in a different way, in such a way that they are coupled at the two ends? And I put them in parallel. What happens to the spring constant then? So here the spring constant is halved. Spring constant here, doubled. Okay. So what we have done here in a simple way is taken objects which have elastic properties, very simple elastic properties in this context, And we've connected them in different ways, and we see that depending on how we connect them, you get different effective spring constants. So a network is some large object consisting of millions, billions of connected springs of various types, connected in a variety of different ways. And one of the physics questions we can ask is, so what is the elasticity of this more complicated object? So we can play a few more games of this type. Let's see if we can ask, well, we can ask this as a homework question. So we now connect springs in this way. We can calculate the effective spring coefficient by combining various these laws again. A simple calculation. Any of you have a feeling what will happen if I change this scenario to this one? It is the same, yes. It's the same if these springs are identical. It's not the same if these springs are not identical. Okay. So we call this a crosslink. So we're just simply linking two elastic linear objects, strings or filaments or polymer chains, together in order to form a crosslink. This is the kind of scenario, this is how one would start thinking about what's happened when Goodyear introduced sulfur into the latex system that he was working on. The sulfur causes crosslinks. It links two different strands to each other and forms a network. We can also think about it in different ways. Without the crosslink, I might be able to pull this system in the horizontal direction. If I were to think about pulling it apart in the vertical direction, of course, you have no, since there's no connection, these two springs can in principle move independently. If you were to think about this one, though, it has a completely different response to that system in the vertical direction. So as soon as you start introducing networking, all of these forces and the constraints of the networking start coupling to each other. We can play nice games on this and think about geometries very similar to the tree network. We can think about taking two springs in parallel, connecting them to a single spring in series, and we can think about extending this idea into something like a tree and continue this elastic game. In this case, one can again calculate how the eventual elastic properties of such a tree-like structure reaches some limit if you fix all of these bonds at a certain point. But once again, depending on which part you pull on, you might have different force expressions. If I started only pulling on this part of the spring and let the others be free, then I'd see just a few springs in series. If I pulled all of them, I'd sample the force and the elastic profile of the tree structure. So we really have to be very precise about how we start thinking about our systems in order, for example, as one of the questions, to determine the elastic properties. Okay. Thinking about these ideas that we introduce something such as crosslinks and that we have polymer chains, what are these sort of obvious parameters that you can think about that might play a role in network elasticity? Well, the properties of the filaments. Okay. What else would definitely influence the elasticity of the network?
The medium in which it's embedded.
The medium in which it's embedded, say it's some kind of fluid, so we're looking at equilibrium statistical physical properties, so that might influence how the chains see each other or the effective interactions. That's a good point.
And the type of crosslink.
The type of crosslink, and even more, something about the crosslinks. Whether they're mobile, the number of crosslinks, the density of the crosslinks. If you have few crosslinks, you might not even have completely have a network that spans the system. If you've just got two crosslinks in a system the size of this room, it's not going to be elastic in the sense that we're thinking about now. Okay. So typically people have then, or scientists have been thinking about how to address this elasticity in terms of the crosslink density. There is another thing, the nature of the crosslinks. You can think about a crosslink linking two strands together so that there are 4 bits of polymer approaching the crosslink. In principle, it's possible to synthesize networks that have the end of one polymer meeting the end of another and the end of a third, and they are linked together, end-linked chains. There can be 3. So the so-called functionality of the crosslink does play a significant role, or will play some kind of function into how strongly the network is linked and what kind of elastic properties it has. So you see the problem becomes dependent on a lot of things. You need to know about the nature of your chains and how they behave under deformation. You need to know about the crosslinks and how many of them there are. And you in principle need to know about the structure of how the network is connected. So the geometry. Which chain is connected to which other chain? So this network is not the same as that network. Now, if you are a chemist, in most cases, although people can really do very clever chemistry, in most cases, you can't really precisely say exactly where each of these polymer chains needs to go. You can't necessarily dictate where each crosslink has to go. So we are faced with the dilemma that we're trying to calculate the properties, say for a theorist, we're trying to figure out the properties of a polymer network, of a connected structure, where we by no means have any information of precisely how it is connected. We have average information, we have the density of crosslinks, we have the number of chains, we have the functionality, but we can't say the 25th bond of chain 2,000,007 is connected to the 376th element of chain 3. Okay? We might if we have a simulation, but theoretically that doesn't make sense. So what we also need to think about is this connectivity. Once you've stirred all of the polymers in the crosslink and made the crosslink by zapping it with light or something like that, we have to figure out how we can address this fact that there is some kind of disorder in the polymer chains. Now we've heard the word disorder in a different context. We've heard about order-disorder transitions. Here, the disorder is just depending on what was the configuration of the system at the moment it was crosslinked, or how did we make the polymer network. There must be something interesting going on. If you take an elastic band, and you take another elastic band, it's almost guaranteed that yeah, polymers are going to be cross-linked in different configurations. Nevertheless, if you take both elastic bands and you put them into some kind of machine and you measure the elastic properties are going to be the same. So what's happening here? We know that there must be different networks. So in the end, these systems behave in a way that they that over large length scales, some of these networking or the geometrical aspects are averaged out. Let's think about the statistical physical formulation of the equivalent of these strings. So let's do equilibrium statistical physics and let's work in the canonical ensemble. So we want to calculate partition function. And we want to look at the simple scenario, for example, of two bits of polymer that are in series. So we have a polymer chain connected to another polymer chain. We fix them, and we, for the moment, although my sketch is two-dimensional, for the moment we're just going to think in terms of one axis. We fix the position of the end of one polymer chain at 0 and the other one at capital X. Okay. We know from the discussions and other lectures already something about the polymer properties. So we know that if you take the beginning position and the final position of a polymer, you square it and you divide it by some factor that has to do with the number of bonds inside that chain. It's the dimensionally correct terminology, that is Gaussian distributed, at least if it's an ideal chain. So we spoke about this ideal chain, the random walk that doesn't see itself, that consists of a certain number of steps. The Gaussian distribution from one position to another. There's some kind of normalization factor that one can calculate by doing the Gaussian integral. Okay. So this would, for example, be the description of one of these chains, and you'd have a similar one for the second chain. So if we want to do the statistical physics in this view of the situation, we're taking a look at this connecting point, but we're not fixing its position. So that's our degree of freedom. So our degree of freedom is x, which can vary over all of the real line. And then we have this polymer connected to that polymer. So we have the correct normalization coefficient for the first polymer, which starts at 0 and ends at the intermediate position. And so we have the first polymer, we have some length scale equal 1 squared. This must be multiplied by an appropriate normalization times the position times the second polymer, which spans the positions from lowercase x to capital X. And it might be a different polymer chain. To make our calculation easy for the moment, we'll just make it the same. Okay. So this is how we calculate the partition function. And then you know from the partition function, you can calculate the Helmholtz free energy. Which is the ubiquitous quantity we've been discussing so far that contains the fundamental competition between order and disorder. So what we want to do is eventually figure out what's the Helmholtz free energy and how does the system answer the question.
Sorry, Kristian, I was wondering, don't you need to constrain the length of the polymer somehow? Or are you just assuming it's infinitely extensible?
Indeed, the random walk, this ideal polymer, is infinitely extensible. We spoke about the mathematical, we heard about the mathematical difficulties involved with finitely extensible chains and with worm-like chains where you find that if you extend, if you think about the extension and the force, you got something like this because there's a maximal extension to any object. Of course, there's a finite number of freely joined worm-like chains, something like that. But our Gaussian polymer just goes on being Gaussian forever and ever. So I can not like that. Let's stay like that. Of course, we're not changing the number of bonds in that flexible chain. So over here, in principle, we can put this point somewhere over there. It still has some contribution to the Boltzmann weight. Of course, it's going to be significantly reduced because this is a Gaussian distribution. Okay, so this represents a very simple Gaussian integral. What's the result of a Gaussian integral? If we integrate Gaussians like this, the result again is Gaussian. Okay, so let's see if we can quickly do the calculation. I did it wrong. So we have whatever the normalization factors are. We simply derive e to the minus x squared to a1 squared okay. Okay, so we can do the Gaussian integral, and apart from those normalization factors, we now get the square root of 2 pi over and we get let's see, we get the maths wrong. Like that, integral, and you see that it immediately gives a Gaussian quarter. Is that correct? Okay, so the free energy, as it depends on capital X in this case, has some contributions from all of these square root terms here which don't depend on X. There we go. Plus something that is the logarithm of x squared, so we've got plus abt 1 over 4a1 squared. Okay. So we see immediately that the free energy, so dimensions of energy, looks very much like our harmonic oscillator. Some energy offset term, free energy offset term is kBt times capital X squared, so this is a parabolic thing. What we have noticed, of course, is that our spring coefficient has just changed slightly. So over here, our individual spring coefficient was proportional to 1 over 2a1 squared. Here it's 1 over 4a1 squared, which corresponds with our normal idea of the springs, and if you put two springs in series, you reduce the spring coefficient. So our statistical physics also does these things correctly, as one would hope. So, our prescription is now clear what we can do with the polymer chain in order to describe our network. So we need to figure out how to describe our polymer chain. Some complicated object. We can put in the crosslinks. For example, these are constraints keeping two bits of the polymer chain. Same thing, it's turned into a polymer network. And in principle, if we do everything correctly, we can calculate the result. Good. So let's again think of a simpler scenario of doing the networking. For the moment, let's not think about what we call crosslinks, but what we call endlinks. So we have three otherwise identical polymer chains swimming around. Okay? We want to network them completely, so to the mix we're going to add two trifunctional linkers. Okay? So functionality F is equal to 3. There are 2 of them, so that must be equal to the 6 ends of the polymer chain. So it's 3 times, so it's 3 times 2, which is the number of ends of each polymer chain. So if we want to make a complete network, we can make a complete network consisting of 3 polymers and 2 trifunctional links. Following way. How many different types of networks can I make? How many networks with different geometries can I make out of this scenario? Any suggestions? I know that some of you know the answer. Some of you, you're not permitted to say. Well, perhaps you shouldn't.
Yeah, I think.
There are 2. Let's see this. So we can take the polymer strands and link them together in this way. Okay. So we have 3 of them in parallel. Or we can take the polymer strands and link them in that way. There's still other options here. You can switch the ends around and you can switch the identity of which polymer does what, but there are these 2 basic configurations that are permissible. Now if we just take the simple-minded kind of view that we are able to do an experiment and pull on this network and pull on that network, you see our description in terms of the numbers of cross-linkers and the number of chains gives 2 different elasticities. Here you would have a much stiffer network, 3 times the individual spring constant of these chains, and here, if you just pull on that, these would essentially be non-functioning parts of the network that don't play a role and don't contribute to the elasticity, and you'd have some object of elasticity with a single spring. Okay. So, let's think about an experiment. We take these networks, all produced by the same recipe, but alternating in their geometry in these 2 ways. Say the probability of this one finding this one. If we do some kind of fantastic chemical reaction, I don't know anything about chemical reactions, but we do something about these we do some chemical reactions and we generate these with probability P and the others with probability minus P. What's the average spring coefficient? So we're thinking about taking these networks and we're very naively putting them between plates like this. And we're all stretching them. So we're taking all of these different copies, we are attaching them, and now I'm pulling this apart. What is the elastic coefficient I'm going to measure? If there are sufficiently many of these networks. Yes.
Do you have an idea of what's the statistical distribution of how many of one kind of connection?
Yes. P is the probability of synthesizing this one, and 1 minus P, the probability of synthesizing the other.
And that's controllable by the experimenter?
Well, by our mental experiment. I'm not quite sure that we'll come to the fact of how we determine P and 1 minus P, for example, in more general setting a little bit later. So, say for a moment we can control this. So then we take all of these Avogadro's number of networks created, we put them in our machine and we stretch them. What is the elasticity? Well, we said that if we were to think about these as very naive springs, not in the completely correct sense. This one has a spring coefficient K, this one has a spring coefficient K. If we view them as springs, remember they're entropic springs, so if they're entropic springs, the spring coefficient has a temperature dependence there. The temperature dependence comes in because, remember, the grounding particles interacting with the polymer chain are hitting it with greater average kinetic energy, and so they can impart on average more force. Okay. How would you calculate it? Well, one idea is to say, well, the effective spring coefficient is just simply the probability of the one spring coefficient times the spring coefficient times the probability of the other scenario times that scenario's spring coefficient. That seems correct, because if we multiply it by the total number of chains, so we have n total network systems, then n times p is the total of species A, and n times 1 minus p is the total number of species B. And if you have springs that are in parallel, you add the spring coefficients. So we can do this, and so we would also need to multiply by n. But on average, per network, you'd have a contribution that is statistically a mixture of these two types of networks. Now, that's just simply using these ideas of springs in order to figure out how a larger selection of networks that you could generate might behave. So we're starting to think about the scenario in the lab. You're mixing all of your stuff, you're zapping it, you're throwing in the chemicals, and out comes something. Not necessarily always precisely controllable in terms of its network structure, but we can in principle start thinking about the fact that if the system is large enough, this network generated by the same process is probably going to behave elastically more or less the same as that network. All that different subunits of it averaged over the whole volume of the network then contribute as if they were averaging something called self-averaging. We won't go to the details of this. Okay, so these are the challenges facing somebody who wants to start assembling networks. We've got the distribution of how these networks can form, and we've got the challenge of calculating the effective spring coefficient. Now I've done this in the high school mechanics picture. Over here, we've had a look at how one can start thinking about more complicated systems in the correct way that we need to think about it as a partition function and a statistical, physical calculation. Okay. So I'm going to present you with the following questions. We should have used the clicker, but I'll give you two options. Say we have some complicated scenario. We calculate the partition function, more complicated than this, but based on the same mathematics, for example, of one scenario, one type of network. We use the same chains with the same degrees of freedom, and we synthesize a second type of network. And as we have over there, this one is synthesized with the probability P1, and this one is synthesized with the probability P2. And once again, we start doing experiments on an ensemble of networks generated in the same way, so that we've got sufficiently many networks to get the statistic right. How, over here, we just did some kind of averaging which was based on counting the numbers of springs. Here we now have the partition function. What's the right way to calculate the average over here? This is not only a rhetorical question. Some of you know the answer. Would you think that if you have the realizations of disorder, you would just calculate some effective partition function? Which is this, or something different? Pick A or B. So who says A? Is that effective? You just average this. No one. Okay. Who says something different? And many of you say neither something different, something not different. Okay. Logical inconsistency over here. Of course, you realize that this is a rhetorical question, so can anybody tell me what this kind of average really represents, and why we don't want it in the kind of scenario that I've described here? You all knew that it was not right. Some of you were not committed to it not being not right. If you want to do the statistical physics correctly and do an average over large realizations of networks, we need to figure this one out, because we can't always just do plain mechanics. What average would you propose? Okay. I'm going to propose that we do an average of the free energy, so that we calculate the free energy in one scenario, the free energy in a second scenario. And we calculate an effective free energy in this way. Let's think about the two things that we're doing in statistical physics. So if we take a general partition function, it's the sum or the integral over the degrees of freedom associated with the system times the Boltzmann weight. Okay? You have to evaluate the degrees of freedom of the system correctly. That's the most important thing, so identifying them and evaluating the degrees of freedom. So, if I now take the partition function of one type of network, so which is a specific description of how the polymer chains are linked to each other. And this specific description play a role over here in the Hamiltonian, which includes, for example, the degrees of freedom associated with these Gaussian polymer chains or whatever filaments there are. Okay? So I could calculate the partition function for one geometry. So I could calculate the partition function for this geometry, or I could calculate the partition function for this way in which the network is connected. There's two very simple example networks. Okay. So one scenario of averaging would be to say, well, I expand this partition function to another one, say called Z prime, and I sum not only about over the polymer degrees of freedom, but also the ways of forming a network. Like this, and I think we think that the Boltzmann weight provides a distribution that perhaps I multiply by the probability of generating a certain network. Okay. In principle, we can then, of course, combine our sums, the network types and the degrees of freedom. Times the probability of the network, like this. And if we wanted to be quite clever and were good enough at maths, we could write down the energy of this network, depending on its geometry, I plus P plus the logarithm of P of the network, at least formally, mathematically, like this, so that the whole thing looks like something in exponential. We can write it down as a new Hamiltonian. Then it looks just like a partition function, which we're calculating in any case with some more degrees of freedom, with some Hamiltonian, some energy, terms describing the configurations of our system. What we're doing is we're treating the network, if we're doing this calculation, we're treating the network and the degrees of freedom, the shapes of the polymer chains, on the same level when we're calculating the partition function. We're both summing over them, and there's an exponential times something. Okay, exponential of something. We're both treating it the same thing. So we're treating the network like a normal degree of freedom. We're treating the network, for example, as in the Ising model we saw yesterday, a spin pointing up or down. Which means that the network configuration 1 or 2 is one that occurs within the system. So there is a configuration of the system that says to switch from that one type of network to another type of network. But that's not what happens in reality. It's a permanent network. If the network is reversible, if all of the polymers can disconnect, they can reconnect it as another network, then this is correct. If they can't disconnect, we can't do that because this is not a degree of freedom that's available to the system. So we have to do another average in that scenario. And that average is, for example, calculating the free energy, or for example, calculating the elastic response of the system, and then averaging it over the network. So here is an example of the kind of average, that's right. So we first measure the free energy for a certain network, then we repeat the experiment for all of the networks multiplied by the incidence of a certain type of network, sum over all possible types of networks in order to calculate the disorder averaged effect of the free energy, which is something different. It is something different because it's a sum over the networks times minus kBt log of z of the network times t of the network. So this is not an average in some other way of the partition functions, it's an average of the logarithm of the partition functions. We are faced with a completely different mathematical challenge here in terms of calculating the average of a partition function, which looks like normal statistical physics. You could use mean field theory and all of the nice other stuff. You usually know, try to approximate this, but the logarithm of something that's complicated in any case and depends in a complicated way on the configuration of the network is a nightmare. Okay. But you need to tackle this nightmare, and we need to do it correctly. The difference between these two scenarios represents two different physical situations. You can have reversible networks forming, so the chains connect, and then a while later they disconnect, and then they reconnect. That's this scenario. If you go and do Goodyear's experiment and you bake the latex with sulfur, then you have to do this calculation because, well, on realistic timescales at least, you're not reconnecting the network in your tire. Okay. This is the difference between what is called an annealed average and a quenched average, where the average is over the disorder, the probability of making a certain type of network. I think my time is almost done. Let me give you an indication of the answer to Jonathan's question. How do we actually start figuring out how to choose what this P of the network is? There's no unique answer, but you can certainly think about what might happen. So imagine some kind of scenario where you've got a long polymer chain of some kind occupying space. You've got some reaction that's going to cross-link this if you illuminate it with strong light. It's doing its polymer chain stuff. So physical physics is an equilibrium. Then you zap it with light, and all at once you've got a bunch of cross-links, and you've turned it into a network. So you've done that transformation in an instant. You've, for example, taken something about the equilibrium configuration of a chain, a typical equilibrium configuration, and wherever the chain touched itself or came into contact with itself, you just added a cross-link. Okay? That might be one scenario of cross-linking. So you can now start thinking about how you choose P. Because P would, in this scenario, be, if you've got a chain, which is in an equilibrium configuration, you know everything about the equilibrium statistical physics, or hopefully you can at least estimate this, where the chain might be touching itself. And if you say that there's a certain likelihood that where the chain makes contact with itself, that a crosslink will be inserted, we've got a way of actually estimating the probability network will be cross-linked by thinking about this scenario. So we can use the ideas of the dynamics, or should really be using the equilibrium scenario if we're doing equilibrium statistical physics, equilibrium scenario out of which we, for example, instantaneously cross-link a network. We can put that in there, and we have calculated Boltzmann weight or probability associated with this usual equilibrium statistical methods, just thinking about the pre-network configuration of the system. So we have that. Okay, so today we spoke about the fact that you can combine these polymers, and that depending on how they're combined, you get different elastic properties. So we need to do an experiment over a large system which somehow samples over all of these possible networks that can form. And that we need to be very careful about the physical situation of how this network is formed, whether it's a reversibly cross-linking network or whether it's a quenched network, in order to finally do the correct calculation for the elastic properties. That's all I have to say.
Example, say with the three-chain system,
yes,
where you get different answers depending on whether you do an annealed average or a quenched average.
I suppose we can work one out. I haven't got one on the top of my mind. I should be able to. We could certainly calculate for the 3 cases. Well, if we just simply take the partition function, say we've calculated everything for the chain. So the anneal average so we've got scenario 1 and scenario 2. And we're constraining, for example, so that we can actually determine the elastic properties, the positions of the 2 crosslinks. So, for example, we're doing the whole partition function sum over polymer degrees of freedom. So, if you're looking at the anneal average, you'd then be saying that the probability of finding scenario 1 times its partition function plus the probability of finding scenario 2 times the partition function would then give you the anneal average. Say these are Gaussian polymers and they don't interact. This is easy to calculate. If we just use our spring analogy, you would have something that is proportional to beta times k, the spring constant, which itself is proportional to the temperature in the flexible polymer case. Z1, you have a spring constant which is 3 times the total extension squared. In the other scenario, you mathematically have you wouldn't see these loops that contribute, so you have just a single chain of spring constant to calculate the total or the anneal average partition function. Okay, I'm throwing away some normalization factors, but they do depend on x. Okay. If I were to do the quenched average, I'd have to calculate the logarithm of these 2 scenarios, multiply them by the probabilities, which is an easy calculation to do because the logarithm of something like this is just p times 3k, okay, minus k t. Which was the original scenario of averaging. And you can see immediately that if you do this and you take the logarithm of the if you take the logarithm of this thing, it's not going to be equal to that. So the difference is already clear on the simple illustrated panel there. Does that answer your question?
I guess so, yeah.
Anything else? Is it time for the coffee break? Before we go to the coffee break, there's some of you who are still owing ICAM some fees, so please come to the front desk just to give the right information.